So what we have discussed yesterday is Laplace transforms and then importance of PDC. What is importance of PDC is to study the dynamics of the responses. So and control of the responses. So what is the, why we need to study PDC is to maintain the variables at a particular value. Suppose if I want to maintain the concentration of distillation column, or let's say if I want to maintain the concentration at the exit of the reactor, or if I want to maintain temperature of the reactor, so like that, the PDC objective is to maintain the variables at a particular value. Why the strength is looks little low today? Why the strength? Oh, IPL finals. So what we can do today is, so we'll start with the first order systems. Is my voice is clear? Okay. So what is meant by first order systems? As we have discussed yesterday, the PDC is two parts: process dynamics and control. There are two parts: process dynamics and control. So first chapter what we are studying is process dynamics. This is chapter 1. So why we need to study the dynamics for the control? Because control is possible when you know the dynamics of the system. For example, suppose if you are talking about the temperature control in a hydrocracker reactor, that is very sensitive system. So that means your controller should be extremely fast to bring back the variable back to, let's say, the previous value. Let's say the hydrocracker temperature is 600 degrees centigrade. Because of some reason, the temperature started to shoot up. At 700 degrees centigrade, there is a runaway reaction. So that means the controller should be able to bring back the value back to 600 before it is touching the 700 degrees. Clear? So the dynamics will tell you how the sensitive or how sensitive the system is. Accordingly, you can design the controller. So without the knowledge of the dynamics, you can't design the controller. So for the design of the runaway reactions, means the reactions will be chains in multiple and you can't control the reactions, is what is runaway reactions. Clear? So what is chapter 1 is, we are talking about the process dynamics, first order system. So how do you study dynamics? How to study dynamics? How to study dynamics? By writing unsteady state model. By writing the unsteady state model. So from the dynamics, how do you study the dynamics is by writing the unsteady state models. So that is the basic objective. So let's take some example. By first order systems means their dynamic models contain, let's say, dy by dt, or let's say df by dt, or let's say dx by dt. Maximum single differential is what is called as first order systems. First order systems means when you write a dynamic model, so it contains only differential equations. So let's study the one example. So how to study the dynamics? One example. Let's take an example of liquid level tank. So liquid level tank. Suppose I'm talking about a simple tank. This is my inlet flow rate. Outlet, you have a control valve, and then outlet flow rate, which is Q. Inlet flow rate is Q naught. So height of the tank, which is, let's say, height of the liquid level, which is H. Now, if you study this, if you understand this system, so suppose if Q naught increases, then what happens to the height of the liquid level? Increases or decreases? Increases. Height of the level increases. Suppose if the Q naught increases, then height of the liquid level also increases. So basically, the height of the level depends on Q naught. So basically what we are talking about here is level controller. I want to maintain the level, or we are talking about a level controller. So that means I want to maintain a level, let's say at a particular H or at a particular set point. Let's say I want to maintain the level at 2 meters height. I want to maintain the level at let's say 3 meters height. I want to maintain the level at say 4 meters height. Like this, I'm talking about the level controller. Clear? Now let's take the cross-sectional area as A. A is cross-sectional area. Q naught is meter cube per hour. Q is also meter cube per hour. The Q depends upon the valve. So this valve, this Q depends on valve. So this Q depends upon the valve. So this Q is equal to, let's say, H by R. So what is R is, let's say, resistance of the valve. What is R is resistance of the valve. R is resistance of the valve. So the valves are multiple types. Some of the valves where, let's say, if my R increases, here what happens is if the resistance increases, Q decreases. Sometimes if the resistance increases, Q also increases. So it depends upon the valve. So this Q equal to H by R, this is something which depends on valve. So you can't fix it on. This is depends upon the valve. So here what I wanted to study is, here we want to study the dynamics of H when, let's say, Q naught changes. This is the thing that I want us to study, the dynamics of H when Q naught changes. Because yesterday we have discussed, PDC comes into picture when there is an unsteady state in the system. Suppose if the systems are working steady state, then there is no need of the entire PDC. PDC comes for unsteady state systems. So you are maintaining the control, or let's say you are maintaining the variables at a particular value. So you are maintaining the variables at a particular set point. So that means if there is a deviation in the level, so the controller. So now I'm not talking about the controllers. The first part is, for the controller design, the first part is you should understand the dynamics. That is where I am. Now let's write the model. Can somebody write the model? Can you write model? Can you write unsteady state model for this liquid level tank? Can you write the unsteady state model for the liquid level? So how do you write the unsteady state model is mass in equal to mass out plus mass accumulation. What is mass in? Let's say rho is density, rho into Q naught and what is mass out is rho q plus what is mass accumulation into what is mass of liquid in the tank divided by dt. So what is rho into q naught equal to rho into q? How do you write mass of liquid in the tank? What is volume of liquid? Cross-sectional area into h. This is what is the volume of the liquid into density divided by dt. Let's assume density is constant. So this density will cancel out, and A is constant, which comes out of the integral. So what you can write it as Q naught equal to Q plus H into dA by, or let's say A into dH by dt. So basically Q naught minus Q equal to A into dH by dt. So this is the unsteady state model. This is unsteady state model. Is everybody clear how do you write unsteady state model? So here you are talking about the mass accumulation. That is why you have written the mass balance. Suppose if you are talking about temperature accumulation, then you will talk about the energy balance. Clear? Cross-sectional area doesn't change. Cross-sectional area will remain same for the tank, no? Now, in PDC, there is special way of derivation. Just follow the derivation. So I will tell you the purpose of this derivation later on, but just follow the derivation how I am doing it. A equal to dH by dt. So Q minus Q naught minus Q equal to A into dH by dt. This is the model. Now, what is this model at steady state? At steady state is Q naught of S, Q of S. At steady state, all the parameters are constant, A into dHs by dt. At steady state, what is your A into dHs by dt? What is the accumulation of mass at steady state? 0. Clear? This is equal to 0. Now what I will do is, let's say this is 1, this is 2. So I'll do 1 minus 2. Then what happens? Q naught minus Q naught of S minus of Q minus QS equal to A into D of H minus HS divided by dt. This Q naught minus Q naught of S, I'll call it as capital Q naught. This Q is nothing but capital Q, which is equal to A into dH by dt. So what is this Q naught? What is this Q naught, Q and H? These are called as deviation variables. These are called as deviation variables. Why they are called deviation? Because they talks about what is the actual value minus what is its value at steady state. Let's talk about this question something like this. Let's say my steady state height is 2 meters. 2 meters is my steady state height, capital H. Then suddenly my height starts to rise. Why? And then it is going to settle at a 3 meters height. 3 meters. This is one dynamic scenario I am talking about. This is one dynamic scenario. My height is at 2 meters and suddenly at time t equal to 0, it starts to deviate. Why we are talking about time t equal to 0? Time t equal to 0 refers when there is a change, or when there is a change, you assign it as time t equal to 0. So your 2 meters height starts to deviate and then is going to reach a new steady state, which is 3 meters. Now, what is your steady state value capital Q is? How do you define it? H minus 2 is what is your capital H. Then what is my capital H? Your capital H is 0. Basically, you are nullifying your initial values. So the deviation variables initial values are always 0, because you have defined the deviation variables as actual value minus its steady state value. So my capital H is 0, and then its time t equal to 0, it is 0, and it starts to deviate, and finally it is going to settle at 1 meter. So this deviation variables makes the, you don't need to have a knowledge of the previous studies, because the dynamics comes into picture when there is a change in the variables. Now, why level is changing? Why the level is changing? Because there is some disturbance to the tank. What is that disturbance? Because inlet flow rate has changed. So inlet flow rate is a disturbance. As a result, what happens? Your height of the liquid level tank is rising. So this is how I have represented one dynamic scenario. It is going to reach 3 meters. But how do you represent this diagram on a capital R deviation variable C? See, your initial values will become 0, and then slowly they will reach a new steady state of 1 meters. So basically the initial value of all the deviation variables, are zeros. Are you getting me? So the reason why I need to produce these dynamic variables is you want to get rid of your initial values, because I can always assume my initial values are zeros. So why you need initial values? Why this is initial value 0? Because you have defined it as actual value minus its initial value. No. Now what is its value here? 0. No, 2 minus 2 0, 2 minus 2 0, 2 minus 2. So finally it is going to settle at 3 meters, but its deviation value is 3 minus 2, which is 1 meter. So in control, whatever you talk is a deviation variables. In the PDC, whatever you talk is a deviation variables. Just understand this concept. I'll give 1 minute time. See, the concept of deviation variables is you are eliminating the initial condition. Suppose if I do this derivation here itself, let's say if I apply Laplace transforms to dH by dt, what is the Laplace transform? S into H of S minus H of 0. H of 0, what is its value? Let's say 2. Whereas if I convert this into deviation variable and apply the Laplace transform, S into H of S minus H of 0, what is its deviation variable? 0, no? So everybody understood the concept of deviation variables? Any doubts here? Now, so I'll go to next one. So now let's take the dynamic model. Deviation variables, how do you define is actual value minus its previous steady state value. So let's take the value Q naught minus Q is equal to A into dH by dt. Suppose if I apply Laplace transform on both sides, then what happens? This is Q naught of S minus Q of S is equal to A into H of S, S into H of S minus H of 0. What is H of 0? 0. Suppose if I don't apply the deviation variables, you should know what is the previous steady state value. Otherwise, you can't do this derivation. Now, what is the final derivation? Q naught of S is equal to Q of S minus A into S into H of S. But what is capital Q? Small q is H by R. Clear? So what is small q minus Hs? Deviation variable is nothing but H by R minus Hs by R. What is Q? Capital Q is nothing but capital H by R. So if we'll apply Laplace transform on both sides, Q of S is equal to H of S by R. So if we apply this one here, so Q of S minus H of S by R, which is equal to A into S into H of S. Can you write this in the form of H of S by, from the above equation, in the form of Kp by tau S plus 1? You should write in this form. H of S by Q naught of S, you should write in this form. You should represent the entire equation in this form. How many of you are from the second year? Any second year people are there? For them, it is slightly difficult to understand this PDC because it is not yet completed. Okay, I see only one person. So I just wanted you to write in the standard form Kp by tau S plus 1. So what do you get is H of S by Q naught of S. What you get this form is R by A into R S plus 1. So what is Kp is, I'll tell you what is Kp and tau. What is the importance? Tau is here. What do you call this H of S by Q naught of S? What do you call this form? This is what you call it as transfer function. In the PDC terminology, this you will call it as transfer function. What is transfer function? This is nothing but a dynamic model. This is nothing but a dynamic model translated into a Laplace space. So basically, what is transfer function? This is basically Laplace transform of output in deviation form divided by Laplace transform of input in deviation form. Laplace transform of output in deviation form divided by Laplace transform of input in deviation form. Clear? So this is what is called as the transfer function. Somebody is asking to, so I just go a little slowly here, because this is something which you need to understand clearly. Tau is AR, Kp is R. What is H of S? Q of S is nothing but the Laplace transforms of height, Laplace transform of inlet flow rate. See, when I apply Laplace transform here, Laplace transform of Q naught is Q naught of S. Laplace transform of Q is Q of S. So I'll tell you tau and Kp what is. Basically, what is transfer function? Laplace transform of output in deviation. So if you see what is dynamic model, Q naught minus Q is equal to dH by dt is dynamic model. This dynamic model is translated. This dynamic model is translated to H of S by Q naught of S equal to R by A into R into S plus 1. So this is translated. In PDC, what happens is all your dynamic models will be translated to transfer functions. Transfer function means it is another form of dynamic model. Transfer function is nothing but the dynamic model. Nothing but the dynamic model. PDC, you talk only transfer functions. In PDC, you talk only transfer functions. Don't let's say misunderstood, or let's say perceptions wise. So don't understood, let's say transfer function is a big term. It is nothing but a general term. So what I did in the transfer function, you started with what? You started with same dynamic model. Then what happens? You have translated your dynamic model to deviation variable. Then you have translated your dynamic model into Laplace domain, which is nothing but your transfer function. So it is remained same, no? So you are not inventing anything new in the PDC. Only thing is you are writing your dynamic models in a convenient form so that it is easy to solve when you are talking about the dynamics. So when we are talking about the dynamics, it is easy to solve. Understood? Is everybody clear? So I will leave you here for 2-3 minutes because you need to understand the derivation and you need to understand this concept of dynamics. See, why I'm going slowly, even though let's say there is no second year students for PDC, because the PDC is something most of the people will feel it as difficult, not because it is really difficult, but because of its terminology, most of the people will feel it as difficult. What is the use of transfer function is something that I will tell later on. No, transfer functions are not steady state models. Transfer functions are unsteady state model. So this S comes into picture, that means it is unsteady state. What is S? It is nothing but another form of T, no? So I'll leave you here for 2-3 minutes. Just understand the derivation and get to the terminal. See, I have not assumed steady state model. No, I just used the steady state model to derive the deviation variables. I am talking about unsteady state model only. I have not used any steady state models here. So whatever I have written in the derivation, if you see anywhere, I started with unsteady state model. You know, this is my unsteady state model. But this is something that I have written just to produce the deviation variables. What is the use of deviation variables is its initial values are always zero. Because in the Laplace, in the PDC, you talk about anything with respect to deviation variables. And then entire terminology, can we proceed further? Is everybody understood the derivation? No doubts. So you have to respond. Anybody has any doubts in the, because this is the basics. If you miss the basics, whatever you study, I will explain what is KP and tau. Don't get confused, but understand whether you are going with the derivation or not. Now, let's take the simple example of, let's say, liquid level tank. Q is equal to 1 meter cube per hour, and then Q naught, Q equal to 1 meter cube per hour. Now the relation is, let's say, H by R. H by R. R is equal to, let's say, assume that R equal to 1. Then what is my steady state height? Set steady state Qs is equal to Q naught of S. We are talking Qs. This is what I'm talking about, let's say, steady state system. Steady state system. So Q of S is equal to H of S by R, which is equal to, what is H of S is 1 meter. So what is the steady state height here is 1 meter height. So there is a steady inlet flow. Now somebody asked me a question. Suppose if suddenly Q naught goes from 1 meter cube per hour to 2 meter cube per hour. Suddenly, how H changes? How H changes? What is the dynamics of height? So that means this is my inlet, which is 1 meter cube per hour. Suddenly changes to 2 meter cube per hour, but for some reason, at time t equal to 0. Then your height will start now. Height is 1 meter. Height will also slowly starts to rise, and then it will settle at some new value. It will settle at some new value. So what is this dynamics of height? What is the dynamics of H? How the dynamics of H changes? Is what is the dynamics of the system that we are doing here? This type of inputs or this type of changes are called as step changes. This is called as step change. That means a parameter suddenly changing from its steady state value to a different value. So let's solve this problem. So this is my problem now. This is my problem. This is my problem. So how do we solve? Let's first understand what is step input. We are talking about the step input. We are talking about the step input. What is step input means? A parameter which is at xs steady state value suddenly changes by a units and then goes to xs plus a. This is at time t equal to 0. This is what is the step input. Now in capital X, in deviation terms, what is deviation term is small x minus xs. So if I plot this one in terms of, let's say, capital X, my capital X is equal to 0 here, and capital X changes by a units, and then it changes by a. So basically, how do you represent capital X is capital X is equal to a. So if you apply Laplace transform, capital X is equal to a by s. So what is the Laplace transform of step input is a by s. So what is step input is a parameter changes from its nominal value of x of s and suddenly changes by a unit and settles at a new value is what is called as step input. I'll just show the previous slide again. I am going to solve this problem. Now, how do you solve this problem? Now, what is the transfer function of the tank? H of s by Q naught of s is equal to R divided by A into R into s plus 1. So, in this problem, A is not given. In this problem, A is not given. Let's say assume that A is equal to, let's say, 2.5 meter cube, some value. Assume the 2.5 meter cube. Now, what is my transfer function h of s? What is R value 1? What is A value 1? 2.5s plus 1. So, what is h of s is by q naught of s is 1 by 2.5s plus 1. So, what is q naught of s here? It is a step input. What is q naught of s is capital Q naught is it starts from 0 and suddenly changes by 1 meter cube per hour because you are not representing the small q, you are representing the big Q. What is the small q? Small q naught, it changes from 1 meter cube per hour and then changes to 2 meter cube per hour. So this translates to capital Q like this. Then what is capital Q? It becomes 1 by S. This is also called as unit step input because the magnitude of change is 1. No. Now what is your h of s? Your h of s becomes 1 by s into 1 by 2.5s plus 1. How do you translate this into in terms of t? How do you translate this in terms of t? Apply the Laplace transforms. H of s is equal to 1 by s, or let's say sum a by s plus b by 2.5s plus 1. So what is a and b? How do you split this into transfer functions? I will represent 1 divided by s into 2.5s plus 1. What is 2.5 is? Area is 2.5, no? How do you split this into partial fractions? Minus 1 by s plus 1 by s minus 2.5 divided by 2.5s plus 1. So this is your partial fractions. This is your h of s. So now what is h of t? If you apply inverse Laplace transform here, what is inverse Laplace inverse of 1 by s plus 2.5 by 2.5s plus 1. So Laplace inverse of, you just change the terms. Laplace inverse of, I'll just write this term as s plus 1 by 2.5 because you have to write in terms of s plus a, no? What is Laplace inverse of 1 by s? 1. What is Laplace inverse of e power minus 2e by 2.5? So this is h of t. So this is my h as a function of time. This is what you call it as dynamics of height. This is what you call it as dynamics of. But still this is capital H. This is not small h. So, but what is capital H? Capital H is nothing but H minus Hs. What is H minus Hs? Hs is 1, no. So this is H minus 1. So H minus 1 equal to 1 minus e power minus t by 2.5. So H is equal to 2 minus e power minus 2 by t.5. So this is what is called as dynamics of height. This particular, this is how you should do the dynamics of transfer functions, or let's say dynamics of the systems. Now if you read the entire problem today's class as it is. I took a liquid level system and I have done I have studied the dynamics of the liquid level system. I have studied the dynamics of liquid level system. Just take time, take 2-3 minutes time and understand. So I'm taking it to all the last slide. Area is given 2.5. In the problem itself, it is given 2.5. It is step input. Meter square, correct. Don't, I will correct it here. It is not, this is meter square. So this is the problem that I started. So I have a steady state system. Suppose if the suddenly if 1 meter cube per hour to 2 meter cube per hour, how H changes? What is the dynamics of height? So then I got the dynamics of height as H equal to 2 into 2.5 as. So this is how you do the dynamics. This is how dynamics is done for a process system. Previous slide. Can some of you create a WhatsApp group? If possible, I'll send the today's class notebooks in that WhatsApp. It's a any G group, email group, or anything. I can send the screenshots to you. Or do you have any group in your? You already have a group. Okay. Somebody says yes, somebody says no. I don't know. Okay. So think about this one. If somebody can take initiative and group, or I will ask the institute people to do some group. Okay, okay. Then let's not digress from the topic. So how do you get 1 by s into 1 by 2.5 s plus 1? So it is r by ar into s plus 1. R is 1, no? A is 2.5. So that is how you got this one. Now, this is what we have done for it. Now, let's take a general first order system. General first order system. A general first order system. You have, let's say, Kp by tau s plus 1. What is its output is y, what is its input is x. Now onwards, I don't need to write, let's say, y of s, x of s also. By default, all the variables in PDC are Laplace transforms. So I'm writing y by x equal to Kp by tau s plus 1. I'm writing y by x equal to Kp by tau s plus 1. What is y means? By default, it is y of s, x of s. Suppose if your x of s is a by s. What is a by s? Step change of magnitude a. Can somebody calculate what is y of t? So I am solving for a general problem. So since I have solved already one problem, so can somebody tell what is y of t? So how do you solve? What is y of s is a by s into kp by tau s plus 1. So now you have to split the partial fractions and then apply the Laplace transform. Inverse Laplace transform. That is where you get the y of t. Oh, sorry. Anybody got answer for y of t? What do you get y of t? It's kp into. This is what is the general step response of a first order system. This is called as step response of a first order system. Clear? So this is a first order system. You took a step input, then you found what is the response. So this is how do you represent this entire system is you have a system something like kp by tau s plus 1. So you have an input which is x, you have an output which is y. This is general representation. Representation of a system in PDC. Representation. What is this one? This is a transfer function, but nothing but what is transfer function is nothing but in your mind you should read it as a dynamic model. This is an input, this is output. Suppose if my input is A by S on this system, then your output is A kp into 1 minus e power minus t by tau, e into t by tau. Clear? So this is how you should read the entire terminology. See, this is output, no? So see in the liquid level tank, this is Q naught, this is H. Don't consider this as an output. In this liquid level tank, I am observing the dynamics of height with respect to Q naught. So my H will become the output. Clear? So, any doubts that you have? Okay. Y of t is inverse Laplace transform. I am not going to solve that. AKP A by S into Kp by tau s plus 1. You have to split into partial fractions and then apply the inverse Laplace transform. So that is I am not going to solve. Q will be the output. Then if Q will be the output, then you have to derive a different transfer function. Q by Q naught of S. For the same liquid level tank, you can have another transfer function Q by Q naught of S. Then what you are doing there is you are studying the dynamics of Q with respect to Q naught. See, what is my observation? Here I want to study the dynamics of H with respect to Q naught. That is why I have derived the transfer function H by Q. If you want to study the dynamics of Q with respect to Q naught, then you should derive the dynamics, let's say Q with respect to Q by Q naught of S. That is the transfer function that you need to derive. Clear? Now another type of input. So let's say what is another type of input? Another types of inputs. So we have studied the step input. So there are multiple inputs. So suddenly, so my flow rate is 1 meter cube per hour. Suddenly it goes to 2 meter cube per hour for a 0 second and it will come back. At time t equal to 0, it goes to 2 meter cube per hour and then come back. This is called as impulse input. This is called as impulse input. Clear? So 1 meter cube per hour, it goes suddenly to 2 meter cube per hour and then comes to 1 meter cube per hour. So this is called as impulse input. Are you clear? So how do you derive the transfer function here for this impulse input? Let's take impulse input. How do you represent this impulse input is capital X equal to, let's say, so how do you represent capital X is, so if I represent this in the form of capital X, it is 0 and at time t equal to 0, it suddenly goes to 1 and it comes back to 0. Or let's say, for example, if I'm talking about a general 1 or let's say A units. So basically it is time t equal to 0. It is 0 and suddenly it goes by A units and then it comes back to 0. So how do you represent this? X is X equal to A into delta Dirac of t. So what is delta Dirac function is? What is delta Dirac function is? Delta of t is 1 when t is equal to 0, 0 when t is not equal to 0. Clear? So what is the Laplace transform of this one? So what is x of s is equal to integral 0 to infinity e power minus st into a into del of t into dt. So when you have delta Dirac function, the integral is nothing but the sum. So you just put t equal to 0. So this is e power minus s into 0, a, which is a. So what is the Laplace transform of x of s here is simple a. When it is a pulse input, it is simple a, impulse input. When it is a impulse input, then it is simple a. What is next one? Suppose if a first order system is disturbed by a impulse input by a impulse, what is the response? What is the response? Then how do you do? Y of s by same. How did you do for step input? Is equal to kp by tau s plus. What is x of s here? Here x of s is simple a because it is impulse input. If it is unit step input, it is a by s. Then what is my a? Akp by tau s plus 1. Then what is my y of t? Laplace inverse of akp by tau s plus 1. What is Laplace inverse of, how do you write this one? This you can write it as akp by tau common 1 by 1 s plus 1 by tau. So akp by tau into e power minus t by tau. So this is what is y of t equal to akp by tau into e power minus t by tau. This is the response for a impulse input. So if you try to see what am I doing today is, I took a first order system. Suppose if my first order system is there are multiple unit changes. No, in a plant you can't restrict to a step input. You can't restrict to a pulse input. You can't restrict. There will be variety of inputs, variety of disturbances. For each variety of disturbance, I am trying to understand how my system responds, which is nothing but the dynamics of the systems. So tomorrow onwards, I am planning to start the class morning at 6 o'clock. So do you have any, maybe 6 to 7, 1 hour at the morning I want to take, if possible 1.5 hours, if the other faculty permits me. Are you okay for 6 o'clock? Or is it too early for you? So that is why I will ask them to adjust. FM will start from 7 o'clock. Evening also I will try to keep, but morning actually I want to complete the syllabus as early as possible. If somebody is saying too early, that means you have not started the preparation. You should be waking up from 5:30. I want to add 1 hour in the morning. Maybe tomorrow I may not take in the evening because I have late meetings in the office, but day after tomorrow onwards, I will take morning and evening all the days. I will talk to management after this, let's say, class. Maybe we'll get an SMS if they agree in the morning also. So somebody is saying I can take in the midnight, but not in the morning. Or just for 5-10 days. So because I want to complete, because this is already late running syllabus. You have supposed to complete the entire syllabus by November. November you should not be taking the classes. Let's see. Tomorrow we will take, and if it finds a big problem for everybody, then we'll think of later on. Okay. So then this is what is the impulse response. What is an impulse? If this kind of, what is another type of input that can affect is, this is pulse input. Pulse input. So I'm directly writing in terms of capital 0, capital X. It changes by A units for, let's say, tau p minutes. Then it comes back to 0 again. So this is a type of input. It goes to A units and it comes back to 0 again. Can somebody tell me what is the Laplace transform of this kind? This is an important problem in maths. For this kind of graph, what is the Laplace transform? So how do you write the Laplace transform of x here? Integral 0 to infinity e power minus st into capital X into dt. So I'll split this into two parts. Integral 0 to tau p e power minus st into what is x into dt plus tau p e power x into dt. So what is this? This is 0. So 0 to tau p e power minus st into dt. So if we solve this integral, then we will get what is the Laplace transform. So what you get is the Laplace transform here is Laplace transform of x here is a by s into 1 minus e power minus tau ps. This is what is the Laplace transform. This is called as pulse input. Suppose if this pulse input affects my system, what is the response? That also you can try. But while solving the problems, I will tell you. What is another type of input is sine input. Sinusoidal input. So how is sinusoidal input is something like this. The value will be fluctuating. So x equal to a sine omega t. So what is the Laplace transform of x is a into w by s square plus w square. So this is sine input. Another type of inputs are ramp input. Something like, let's say x equal to t. Then what is the response? This is something like this. Or x equal to e power t, or x equal to t square. All these are ramp inputs. So that means the parameters, input parameters are continuously changing. So basically we have discussed 4 types of inputs. Here step input, pulse input, impulse input, sine input, ramp input. So for every input, the behavior of the system is different. So for every input, the behavior of the system is different. Like you have, let's say, Kp by tau s plus 1. When the system is forced by A by S, then you have Kpa into 1 minus e power minus t by tau. Same is forced by, let's say, A, then the system response is Kpa by tau into e power minus t by tau. This is what is step. This is what is impulse. Suppose if it is pulse, which is A by S into 1 minus e power minus tau ps, then the response is different. Suppose if it is actuated by AW by S square plus omega square, then the response is different. So this is something which we study in this frequency response. This 4th one is something which we study in frequency response. So, but remember one thing, the system remains same, but the output behavior changes depends upon the input behavior. So the output, third one is I don't need to solve because while solving the problems, I'll tell you a different way of solving pulse input. Clear? So the system is still a liquid level tank. So liquid level tank can have a variety of dynamics based on the input. So that is what input depends upon the input, the behavior of the system is same. So here important one more point is, so if you, this is the output for this input, this is the output for this input. Once again, this output divided by this input, you will get the transfer function. So transfer function is nothing but output divided by input. Suppose if you apply, let's say what I'm trying to say is Laplace transform of Kpa into 1 minus e power minus t by tau divided by a by s, which is Laplace transform of output for the corresponding input, will you get still the same input Kp by tau s plus 1. So Laplace transform of Kpa by tau into e power minus t by tau, so divided by a is still Kp by tau s plus 1. So everything is linked. So this is an output corresponds to this input. This is an output corresponds to this input. So this entire thing matches. So basically what is transfer function is, so why transfer function is same? because the process is same, no? The liquid level tank remains same, but the dynamics of height depends upon how the input is changing. But the liquid level doesn't change, no? The inherent characteristics of the liquid level tank remains same, but the behavior of the output depends upon the input. So the system will never change. Did everybody got? I think I'll stop it here. So we have completed the one part. So that is the first order systems and its dynamics. So tomorrow we will solve the problems. So basically what I'm trying to say is the systems remain same. So that is why the transfer functions remain same. So the input and output keep on changes. So this is a beautiful example. My transfer function kp by tau s plus 1 remains same. But if I give the input a by s, its input, tan input and all will not be there. So ramp inputs, I'll explain this one. If the system is forced by a step input, then the response is like this. If the system is forced by a, then the response is like this. So basically, depends upon the response, this changes. Tan input, see, you can do the derivation for tan input, cos input, sin input, and everything. So basically, you have a transfer function in your hand. But popular inputs that I am discussing are step input, impulse input, pulse input, ramp input. So, and ramp inputs are something which are increasing continuously as a function of time, are ramp inputs. So I'm open for your doubts. If you have any doubts, I can take your doubts. So, but you will get an SMS right now. I will talk to the management and tell you tomorrow morning 6 o'clock class. But tomorrow definitely evening I may not be possible to take class because I have a meeting till 7:30. But I request you to somebody create WhatsApp group or something else so that I can send every day's this screenshots to all. Yeah, I can ask all institutes to create the group so that I can also send all the messages. So if you have any doubts, we are open for doubts. I can take 10 minutes doubts. So previous year questions are sufficient. You don't need to solve any other questions. So not required also. If you have enough energy, then solve the textbook backend questions. See, all these inputs are types of inputs that is possible in the plant, but in the plant you may not have exactly the No, I do not teach MTO. There is no tips for remembering the formulas. Tips for remembering the formulas is revisions. Yeah, pulse input is a combination of two-step inputs. You can write it like this. Nyquist plots is not there in the guide syllabus. Don't worry. Which last part? So what I'm trying to say in the last part is, this is a system. This system is forced by step input. This is the response. This system is forced by impulse input. This is the response. So the system remains same, depends upon the input, output changes. Yeah, you can call it rectangular pulse input or something. So I will ask the institute to create one group. Let's see how it happens. Any doubts?